Something is hiding in the glow of one of the most famous stars in the night sky. For decades, astronomers watched Betelgeuse pulse and dim in ways that defied explanation. They proposed dust clouds, internal convulsions, even the death throes of a dying giant. But the truth turned out to be far more elegant and far more surprising. Betelgeuse is not alone. High in the constellation of Orion, marking the hunter's left shoulder, burns a star so immense that if you placed it where our sun sits, its outer atmosphere would swallow Mercury, Venus, Earth, Mars, and reach beyond the orbit of Jupiter. This is Betelgeuse, a red supergiant in the final stages of its stellar life, a cosmic beacon visible to every human civilization that has ever looked up at the winter sky. The ancient Arabs called it the hand of the giant. The Japanese saw it as the star of the warrior. For astronomers, it has always been a puzzle wrapped in mystery, surrounded by an enigma of flickering light. The story of BetelBuddy begins not with a discovery, but with a frustration. Since systematic observations began in the 19th century, scientists noticed that Betelgeuse does not shine with steady light. It breathes, pulses. It dims and brightens in complex rhythms that seem to follow multiple overlapping cycles. The most obvious of these takes roughly 400 days to complete. Every 400 days or so, Betelgeuse reaches a peak brightness, then fades, then climbs back again. This cycle has repeated with remarkable consistency for as long as we have been watching. But here is what bothered astronomers for generations. Red supergiants do pulsate. This is well-established physics. As these enormous stars age and their cores contract, their outer layers become unstable. They swell and shrink like a beating heart, and this changes their brightness. The problem is that the pulsations predicted by stellar models did not match what Betelgeuse was actually doing. The 400-day cycle was too long, too regular, too clean. Something else had to be going on. Throughout the 20th century, various theories emerged to explain the anomaly. Some suggested that Betelgeuse had an unusually complex internal structure, with multiple pulsation modes interfering with each other to produce the observed pattern. Others proposed that giant convection cells on the star's surface, each one larger than the orbit of Earth, were rising and falling in ways that modulated the light. Still others wondered if circumstellar dust, material ejected from the star's outer layers, might be periodically obscuring our view. Each of these explanations had merit. Each could account for some of what we observed, but none of them felt complete. There was always something left over, some residual pattern in the data that refused to be explained away. And then came the great dimming. In late 2019, Betelgeuse began to fade. This was not unusual in itself. The star dims all the time as part of its natural cycles. But this dimming was different. By February 2020, Betelgeuse had dropped to less than 40% of its normal brightness. It was the faintest the star had been in over a century of recorded observations. For a few dramatic weeks, headlines around the world proclaimed that Betelgeuse might be about to explode. Social media filled with speculation about an imminent supernova. Astronomers, more cautious by training, urged patience and continued observation. The supernova did not come. By April 2020, Betelgeuse had begun to recover its brightness, and within months it was back to normal. Subsequent analysis revealed that the great dimming was caused by a combination of factors. A massive plume of hot gas had erupted from the star's surface, cooling as it rose and condensing into a cloud of dust that partially blocked our view. This event coincided with a minimum in the star's natural pulsation cycle, amplifying the dimming effect. It was dramatic, it was newsworthy, and it taught us something important about how red supergiants lose mass into space. But the great dimming also did something else. It drew unprecedented attention to Betelgeuse. Telescopes around the world and in orbit turned their instruments toward Orion's shoulder. New observation campaigns were launched. Archives of historical data were reanalyzed with fresh algorithms. And in this intense scrutiny, patterns began to emerge that had been overlooked before. The key insight came from a careful study of the 400-day cycle. When astronomers looked closely at the timing of this brightness variation, they noticed something subtle but significant. The cycle was not perfectly periodic. Sometimes Betelgeuse reached its maximum brightness a few days early. Sometimes it arrived a few days late. These deviations were small, easy to dismiss as measurement error or random fluctuation. But they were not random. They followed their own pattern, a secondary rhythm superimposed on the primary cycle. This is where we need to understand a concept called orbital mechanics. When two objects orbit each other in space, they do not simply sit still while one circles the other. Both objects actually orbit around their common center of mass, a point called the barycenter. For a system like the Earth and the Moon, the barycenter lies inside the Earth about 1,000 miles below the surface. For a system like the Sun and Jupiter, the barycenter lies just outside the Sun's surface. The more massive the companion, the more the primary star wobbles around this shared center. Now imagine Betelgeuse, bloated and ancient, carrying on its eternal pulsation. If there were a companion star orbiting nearby, Betelgeuse would wobble. This wobble would carry it slightly toward us, then slightly away, then toward us again. And because of the Doppler effect, this motion would shift the timing of when we see the star's brightness peaks. When Betelgeuse is moving toward us, the light takes slightly less time to arrive, and we see the maximum earlier than expected. When it is moving away, the light is delayed, and the maximum comes late. This is exactly the pattern that emerged from the data. The small timing variations in the 400-day cycle were consistent with Betelgeuse being tugged back and forth by an unseen companion in an orbit of roughly 2,200 days. 6 years. 6 years for this hidden object to complete one circuit around the giant star. The evidence was compelling but indirect. Timing variations alone could potentially have other explanations. What the scientific community needed was independent confirmation, a separate line of evidence pointing to the same conclusion. And in 2025, that confirmation came. Using a combination of advanced spectroscopy and interferometric imaging, astronomers detected the direct signature of a second object in the Betelgeuse system. The companion is small, at least by the standards of stellar astronomy. Current estimates suggest it is somewhere between 1 and 2 solar masses, making it either a low-mass star or possibly a dense stellar remnant like a white dwarf or neutron star. It orbits Betelgeuse at a distance of roughly 12 astronomical units, about the same distance that separates Saturn from our Sun. The Discovery team named it BetelBuddy, a playful acknowledgement of the long partnership this object has maintained with its famous host. The name caught on immediately. Within weeks, BetelBuddy had become a fixture of astronomical discourse, a new character in the ongoing story of one of the sky's most celebrated stars. But what exactly is BetelBuddy? And how did it come to be where it is? These questions take us deep into the physics of stellar evolution and the dynamics of binary star systems. Most stars in our galaxy are not solitary like our Sun. They come in pairs, triplets, and even larger groups, bound together by gravity and orbiting around shared centers of mass. Binary stars are so common that astronomers estimate more than half of all Sun-like stars have at least one companion. For more massive stars, the fraction is even higher. Perhaps 80% of stars like the one that became Betelgeuse are born with siblings. When a binary system forms, the two stars condense from the same cloud of gas and dust. They may start out with similar masses or very different ones, depending on the random details of how the cloud fragments and collapses. Once formed, the pair settles into an orbit that can remain stable for billions of years, each star evolving according to its own mass and composition. Here is where things get interesting. More massive stars live fast and die young. A star with 10 times the mass of the Sun burns through its nuclear fuel in perhaps 20 million years, while a star with half the Sun's mass can shine steadily for over 100 billion years. In a binary system with unequal masses, the heavier star will age much faster than its lighter companion. Betelgeuse started its life as a massive blue star, probably around 15 to 20 times the mass of the Sun. It burned brilliantly and quickly, exhausting the hydrogen in its core in a cosmic eye blink. As the core contracted and heated up, the outer layers of the star expanded and cooled, transforming Betelgeuse from a compact blue furnace into the swollen red giant we see today. This expansion was enormous. Betelgeuse grew from something a few times the size of our Sun to something nearly 1 billion miles across. Meanwhile, BetelBuddy, starting with a much smaller mass, has evolved far more slowly. If it is indeed a star rather than a stellar remnant, it may still be burning hydrogen in its core, barely changed from its original state. It has watched its giant sibling transform from a blue star to a red giant, and it will likely outlive Betelgeuse by billions of years. The relationship between these two objects has shaped the 400-day cycle that astronomers have puzzled over for so long. Here is how it works. As BetelBuddy orbits Betelgeuse, its gravity exerts a tidal pull on the giant star's atmosphere. This tidal force is not strong enough to tear the star apart, but it is strong enough to create a rhythmic disturbance in the outer layers. This disturbance amplifies and stabilizes certain natural pulsation modes while suppressing others. Think of it like pushing a child on a swing. If you push at random times, the swing moves chaotically. But if you push in rhythm with the swing's natural period, you can build up large, stable oscillations. BetelBuddy acts as a cosmic pusher, its orbital motion providing a regular gravitational nudge that locks Betelgeuse's pulsations into the 400-day period we observe. This mechanism, called tidal forcing, had been proposed theoretically before, but Betelgeuse was the first case where astronomers could see it in action. The discovery of BetelBuddy turned a theoretical possibility into an observed reality, providing a textbook example of how stellar companions can influence the internal dynamics of giant stars. But the influence runs both ways. As Betelgeuse pulsates and sheds material into space, some of that material inevitably encounters BetelBuddy. The companion plows through the thin outer atmosphere of the giant, creating shock waves and disturbances that may generate their own observable signatures. Some astronomers have proposed that variations in the X-ray and ultraviolet emission from the Betelgeuse system could be caused by BetelBuddy's passage through denser regions of the stellar wind. This interaction also has implications for the future evolution of the system. As Betelgeuse continues to expand and lose mass, the dynamics of the binary orbit will change. The two stars may draw closer together or drift farther apart, depending on exactly how the mass loss occurs. In extreme scenarios, BetelBuddy could spiral inward and eventually merge with its giant host, releasing enormous amounts of energy and potentially triggering exotic phenomena. But the most dramatic event in this system's future is not the merger. It is the supernova. Betelgeuse will explode. This is not speculation or prediction. It is the inevitable endpoint of a massive star's evolution. When a star like Betelgeuse exhausts the nuclear fuel in its core, there is nothing left to hold up the enormous weight of the overlying layers. The core collapses in a fraction of a second, compressing from something the size of the Earth to something the size of a city. The infalling material bounces off this newly formed neutron star or black hole, generating a shock wave that tears the star apart from the inside out. The explosion will be visible from Earth, even though Betelgeuse lies some 650 light-years away. For a few weeks or months, a new point of light will blaze in the sky, bright enough to see in daylight, bright enough to cast shadows at night. It will be the most spectacular astronomical event in human history, a once-in-a-civilization experience that will be watched and remembered for generations. When will this happen? The honest answer is that we do not know. Betelgeuse could explode tomorrow. It could hold together for another 100,000 years. In astronomical terms, both of these timescales are essentially instantaneous, but for human purposes, the uncertainty is profound. We are watching a star that is certainly in the final stage of its life, but we cannot say exactly when the end will come. The discovery of BetelBuddy adds a new dimension to this waiting game. The companion star will not prevent the supernova or significantly alter its timing, but it will affect what happens afterward. When Betelgeuse explodes, the material ejected by the explosion will slam into BetelBuddy with tremendous force. Depending on the companion's nature and position, this collision could strip away its outer layers, shock heat its atmosphere, or even disrupt the star entirely. If BetelBuddy survives the explosion, it will find itself in a very different situation. The supernova will leave behind either a neutron star or a black hole, depending on exactly how much mass remains in the collapsing core. This compact remnant will be tiny compared to the original Betelgeuse, perhaps 15 miles across for a neutron star or essentially a point for a black hole. But it will still exert gravitational pull on BetelBuddy, and the two objects will remain bound together in a new kind of binary system. Such systems are not hypothetical. Astronomers have observed many binaries containing a normal star and a compact remnant. These systems often produce spectacular phenomena as material flows from the normal star onto the neutron star or black hole, heating up to millions of degrees and emitting intense X-rays. BetelBuddy, currently an obscure companion hidden in the glare of its giant host, may someday become the primary star in its own exotic binary system. But we are getting ahead of ourselves. Let us return to the present and consider what BetelBuddy can teach us about stellar astronomy more broadly. The Betelgeuse system is not the only giant star suspected of hosting companions. In fact, the more closely astronomers look at red supergiants and asymptotic giant branch stars, the more evidence they find for multiplicity. Many of these objects show photometric variability that cannot be explained by single-star models. Many show spectroscopic signatures suggesting the presence of additional objects. and many are surrounded by circumstellar environments that show evidence of gravitational disturbance. BetelBuddy represents a breakthrough in our ability to detect and characterize such companions. The techniques used to find it, combining long baseline timing analysis with advanced spectroscopy and interferometry, are applicable to many other systems. Already, teams around the world are applying these methods to other notable giants, searching for hidden companions that might explain their observed behavior. The implications extend beyond just understanding individual stars. Binary interactions play a crucial role in many of the most important and dramatic phenomena in astrophysics. Supernovae, neutron star mergers, gravitational wave sources, gamma-ray bursts, and the production of heavy elements all involve stars interacting in pairs or groups. The more we understand about how binary systems evolve, especially those containing massive stars, the better we can predict and interpret these cosmic events. Consider the question of supernova rates. Astronomers have long struggled to reconcile the observed rate of supernova explosions in our galaxy with theoretical predictions based on stellar evolution models. Some of this discrepancy may come from our incomplete understanding of binary interactions. Stars in close binaries can exchange mass, merge, or be stripped of their outer layers by their companions, all of which affects whether, when, and how they explode. BetelBuddy, by providing a detailed case study of a massive star binary, helps calibrate these models. There is also the question of stellar mass loss. Red supergiants like Betelgeuse shed enormous amounts of material into space through stellar winds and episodic ejections. This mass loss affects the star's subsequent evolution, the composition of the interstellar medium, and the eventual supernova explosion. But the mechanisms driving this mass loss are not fully understood. Does it happen smoothly and continuously, or in bursts and eruptions? How much material is lost in total, and what determines the rate? BetelBuddy may provide answers. The companion's gravity could enhance mass loss by raising tides that lift material away from the giant's surface. Alternatively, the companion might sculpt the outflowing wind, creating spiral patterns and density enhancements that affect how the material disperses into space. By studying how BetelBuddy interacts with the circumstellar environment, astronomers can learn about mass loss processes in ways that would be impossible for a single star. Let us take a step back and appreciate the observational challenges involved in studying this system. Betelgeuse is very bright, one of the brightest stars in the night sky, which you might think would make it easy to study. But brightness brings its own problems. The star is so luminous that it saturates many modern astronomical detectors, which are designed for much fainter targets. Observing Betelgeuse often requires special techniques, neutral density filters, or purpose-built instruments that can handle the flood of photons. The angular size of Betelgeuse presents another challenge. Most stars, even through the largest telescopes, appear as simple points of light. Betelgeuse is different. It is so large and so close, relatively speaking, that we can actually resolve its disk. We can see surface features, spots, and bright regions moving across the face of the star. This sounds like an advantage, and in some ways it is, but it also complicates the analysis of brightness variations. When you can see the surface, you have to account for how it changes, not just track the total light output. The circumstellar environment adds yet another layer of complexity. Betelgeuse is surrounded by shells and arcs of ejected material, dusty clouds that absorb and scatter the star's light. Some of this material lies close to the star, within a few stellar radii, while other structures extend out to several hundred astronomical units. These structures evolve over time, sometimes quite rapidly, and their changing properties can mimic or mask the signals from the star itself. Into this complicated picture, we now add BetelBuddy. The companion is much fainter than Betelgeuse, perhaps 10,000 times less luminous. Detecting it directly against the glare of the giant is like trying to see a firefly next to a searchlight. The technical achievements required to tease out its signature from the overwhelming light of its host represent decades of progress in astronomical instrumentation. Spectroscopy has been one of the key tools. By spreading starlight into its component wavelengths, astronomers can identify the chemical fingerprints of different elements and molecules. They can also detect Doppler shifts caused by motion toward or away from us. If a star is wobbling due to an orbiting companion, this wobble shows up as a periodic shift in the spectral lines, back and forth, blue to red and red to blue, in time with the orbit. For a system like Betelgeuse BetelBuddy, the spectroscopic detection is extraordinarily difficult. The wobble velocity is small, perhaps a few hundred meters per second, which corresponds to a very slight shift in wavelength. And the spectrum of Betelgeuse itself is complicated, filled with features from the star's extended and turbulent atmosphere. Identifying the small periodic signal from BetelBuddy required sophisticated statistical techniques and many years of accumulated data. Interferometry has provided complementary information. By combining light from multiple telescopes separated by significant distances, astronomers can achieve angular resolution far beyond what any single telescope could provide. This technique has been used to image the surface of Betelgeuse directly, revealing the enormous convection cells that roil across its face. More recently, it has been applied to search for asymmetries in the light distribution that might indicate the presence of a companion. The interferometric data that contributed to the BetelBuddy discovery came from several facilities, including the Very Large Telescope in Chile and the Chara Array in California. These instruments can resolve structures less than a millisecond across, about the apparent size of a quarter seen from 4,000 miles away. At this resolution, the influence of BetelBuddy on the geometry of the Betelgeuse system becomes detectable, even if the companion itself cannot be imaged directly. Historical observations have also played a crucial role. Betelgeuse has been observed systematically for well over a century, with measurements of its brightness dating back to the 1800s. This long baseline of data allows astronomers to track variations that occur on timescales of years or decades, variations that might be invisible in a few years of intensive study. The 2200-day orbital period of BetelBuddy, for instance, would require at least 6 years to complete a single cycle. Without decades of accumulated data, the pattern might never have been recognized. Archives from earlier generations of astronomers are treasure troves for this kind of work. Photographs taken with 19th and early 20th century telescopes, originally recorded on glass plates, have been digitized and measured with modern precision. Variable star observers, many of them amateur astronomers keeping meticulous records year after year, have contributed invaluable data that professional surveys often lack the continuity to provide. The BetelBuddy discovery stands on the shoulders of countless observers who never imagined that their painstaking measurements would help reveal a hidden star. Now let us consider BetelBuddy itself in more detail. What kind of object is it? This question is not fully settled. The observations constrain its mass to somewhere between 1 and 2 solar masses, but within that range, several possibilities remain. The most straightforward interpretation is that BetelBuddy is a main sequence star, an object similar in some ways to our Sun but somewhat more massive and luminous. A star at the upper end of the mass range, around 2 solar masses, would be a spectral type A star, white-hot and perhaps twice as bright as the Sun. At the lower end, around 1 solar mass, we would have a near twin of our own star, yellow and steady. Such a companion would have formed alongside Betelgeuse from the same natal cloud, would have been burning hydrogen in its core for the entire 10 million year lifetime of the system, and would have remained relatively unchanged while its companion bloated into a red supergiant. This scenario is entirely consistent with what we know about binary star formation and evolution. But there are other possibilities. BetelBuddy could be a white dwarf, the dense remnant of a star that has already completed its evolution. If the Betelgeuse system started as a triple rather than a binary, one of the original companions might have already lived out its life and collapsed. White dwarfs with masses around 1 solar mass are common, and their faint glow would be difficult to detect against the brilliance of Betelgeuse. Even more exotically, BetelBuddy could be a neutron star, the collapsed core of an even more massive star that exploded in a supernova millions of years ago. This scenario is less likely because such an explosion would have dramatically affected the system dynamics, but it cannot be completely ruled out. A neutron star in a wide orbit around Betelgeuse would be essentially undetectable through most techniques, revealing itself only through its gravitational influence. Future observations will help distinguish between these possibilities. If BetelBuddy is a main sequence star, it should contribute detectable light to the system, light that could be isolated and analyzed through careful spectroscopy. If it is a white dwarf or neutron star, different signatures would apply. Astronomers are already planning observation campaigns designed to characterize the companion more precisely. Whatever BetelBuddy turns out to be, its existence changes our understanding of the Betelgeuse system in fundamental ways. For decades, Betelgeuse was treated as a single star, and its properties were modeled accordingly. Now we know that everything we see is influenced by a cosmic partner whose gravitational embrace has shaped the pulsations, the mass loss, and perhaps even the internal structure of the giant. This realization extends beyond Betelgeuse to other famous stars. How many other apparently single giants might be hiding companions? How much of what we attribute to intrinsic stellar properties might actually be the result of binary interactions? These questions are driving a new wave of observational and theoretical work. Consider Antares, the red supergiant in Scorpius, Betelgeuse's rival for the title of most famous dying star. Antares is known to have a blue companion, visible in small telescopes as a contrasting point of light near the giant. But could there be additional undiscovered companions? The techniques that revealed BetelBuddy are now being applied to Antares and other similar systems. Or consider the mysterious behavior of other pulsating giants, stars that show complex variability patterns that do not quite fit single-star models. Some of these may harbor companions that modulate their oscillations, just as BetelBuddy does for Betelgeuse. The field is ripe for discovery. There is also a connection to the emerging science of gravitational wave astronomy. When massive stars and binary systems reach the end of their lives and collapse into neutron stars or black holes, the resulting compact objects can spiral together and merge, producing ripples in spacetime that propagational across the universe. Facilities like LIGO and Virgo have detected dozens of these mergers, opening a new window on the cosmos. Understanding the progenitor systems of these mergers, the massive binaries that produce neutron stars and black holes, is crucial for interpreting the gravitational wave signals. BetelBuddy provides a snapshot of such a system at an earlier stage, before the catastrophic events that transform ordinary stars into exotic remnants. By studying systems like Betelgeuse BetelBuddy, astronomers can calibrate their models of binary evolution and make better predictions about what the gravitational wave detectors will see. The Betelgeuse system also offers a natural laboratory for studying stellar atmospheres in extreme conditions. The outer layers of Betelgeuse are cooler than our Sun but far more extended, creating an environment where molecules can form, dust can condense, and complex chemistry can take place. This circumstellar environment is shaped by pulsations, by mass loss, and now we know by the gravitational presence of BetelBuddy. When BetelBuddy orbits through the outer atmosphere of Betelgeuse, it creates disturbances that might be detectable as localized changes in temperature, density, or composition. These disturbances could be observed using high-resolution spectroscopy or interferometric imaging, providing information about both the companion and the atmosphere it moves through. It is a cosmic probe, sampling the extended envelope of a giant star from the inside. Let me share some numbers that help put the Betelgeuse BetelBuddy system in perspective. The orbital period of BetelBuddy, approximately 2,200 days or about 6 years, is comparable to Jupiter's orbital period around the Sun, but the distances involved are vastly larger. BetelBuddy orbits at roughly 12 astronomical units from the center of the Betelgeuse system, which sounds large until you remember that Betelgeuse itself, when at maximum extension, has a radius of perhaps 5 or 6 astronomical units. The companion is not orbiting far outside the giant star. It is skimming through the outermost layers of its atmosphere. This close passage has consequences. Material from Betelgeuse can flow onto BetelBuddy, potentially forming an accretion disk around the companion. If BetelBuddy is a compact object like a white dwarf or neutron star, this accretion could produce detectable X-ray emission. If it is a normal star, the accreted material might alter its spectral appearance or drive outflows of its own. The interaction is intimate and ongoing. The mass of Betelgeuse itself is still somewhat uncertain, with estimates ranging from about 12 to 20 solar masses. This uncertainty affects calculations of the orbital dynamics, the tidal interactions, and predictions for the eventual supernova. As techniques improve and more data accumulates, these estimates will be refined, and our picture of the system will come into sharper focus. Let us turn now to the cultural and historical significance of Betelgeuse and what the discovery of BetelBuddy adds to this story. Betelgeuse has been a fixture of human consciousness for millennia. Its distinctive red-orange color, clearly visible to the naked eye, made it a marker and a mystery for ancient peoples around the world. In Western astronomy, Betelgeuse takes its name from an Arabic phrase that has been variously translated as the hand of the central one or the armpit of the giant. The star marks the right shoulder of Orion in traditional constellation diagrams, one of the most recognizable patterns in the night sky. Orion the hunter strides across winter skies in the northern hemisphere, his belt of 3 aligned stars serving as a signpost for stargazers of all experience levels. Indigenous cultures around the world incorporated Betelgeuse into their own traditions. For some Aboriginal Australian groups, the stars of Orion represented a canoe, with Betelgeuse and Rigel marking figures at either end. In Hawaiian tradition, Betelgeuse was known as Kauluakoko, and its color was associated with specific meanings in the rich navigational lore of Pacific Islanders. Every human society that developed astronomy had a story about this brilliant red star. Modern science has added new layers to this story without diminishing its wonder. We now know that Betelgeuse's red color comes from its cool surface temperature, just over 3,000 degrees, compared to our Sun's 5,500 degrees. We know that its variability results from complex physical processes in its interior and atmosphere. We know that it represents a stage of stellar evolution that our own Sun will never reach, because the Sun lacks the mass to become a red supergiant. And now we know that this celebrated star has been dancing with a hidden partner since before life emerged on Earth. The discovery of BetelBuddy adds a romantic element to the scientific narrative. For millions of years, this pair has circled together through the galaxy, bound by gravity, shaping each other's fates. When Betelgeuse was young and blue and compact, BetelBuddy was there. As Betelgeuse aged and expanded, BetelBuddy stayed close, adjusting its orbit as conditions changed. And when Betelgeuse finally explodes, BetelBuddy will be there to witness it, bathed in the radiation of its partner's death throes. There is something poignant in this cosmic companionship, something that resonates with human experience, even though the timescales and distances defy imagination. We too seek companions. We too age and change while maintaining our connections. The universe, it seems, is full of partnerships at every scale. This brings me to the future, both the future of the Betelgeuse BetelBuddy system and the future of our attempts to understand it. The James Webb Space Telescope, the most powerful space observatory ever built, is now operational and capable of studying Betelgeuse and its environment in unprecedented detail. Webb's infrared vision can peer through dust that blocks visible light, revealing structures and processes invisible to ground-based telescopes. Observations of Betelgeuse with Webb have already produced remarkable results, showing the complex dusty environment around the star with clarity never before achieved. Future observations will specifically target the BetelBuddy interaction, looking for signatures of the companion's passage through the stellar wind and searching for evidence of accretion or mass transfer between the stars. Ground-based facilities are also advancing. The extremely large telescope, currently under construction in Chile, will have a primary mirror nearly 40 meters across, giving it the light-gathering power and resolution to directly image planets around nearby stars. It will also be able to study the surfaces of resolved giants like Betelgeuse with extraordinary detail, potentially picking out the influence of BetelBuddy on the stellar atmosphere directly. Theoretical modeling is advancing alongside observations. Sophisticated computer simulations can now follow the evolution of binary stars through multiple stages of interaction, from formation through mass transfer through eventual explosion or merger. These simulations make predictions that can be tested against observations of systems like Betelgeuse BetelBuddy, closing the loop between theory and data. One of the most intriguing theoretical questions concerns the final fate of BetelBuddy after the supernova. Depending on the details of the explosion and the properties of the companion, several outcomes are possible. The supernova might unbind the system entirely, sending BetelBuddy hurtling off into space as a runaway star, carrying the chemical products of the explosion in its contaminated atmosphere. Alternatively, the system might remain bound, with BetelBuddy entering a close orbit around the neutron star or black hole remnant of Betelgeuse. In the latter scenario, the resulting system could evolve through mass transfer to produce exotic phenomena. A neutron star accreting from a normal stellar companion is called a low-mass X-ray binary if the companion is small, or a high-mass X-ray binary if it is large. These systems are among the brightest X-ray sources in the sky, laboratories for studying physics under extreme conditions. If BetelBuddy ends up in such a configuration, astronomers generations hence might study it as a completely different kind of object than we know today. The possibility of a runaway BetelBuddy is equally fascinating. Runaway stars, unbound from their birthplaces by supernova explosions or gravitational encounters, are found throughout the galaxy. Some travel at hundreds of kilometers per second, fast enough to eventually escape the Milky Way entirely. If BetelBuddy becomes a runaway, it might be identifiable by its peculiar velocity and unusual chemical composition, carrying isotopes produced in the Betelgeuse supernova as atmospheric pollutants. There is something thrilling about the idea that a star we can name and characterize today might still be trackable millions of years from now, transformed by cosmic events into something new but still bearing the marks of its origin. Astronomy often deals with timescales that dwarf human experience, but in cases like this, we can trace the threads of connection across vast expanses of time. Let me return to the present moment and reflect on what the BetelBuddy discovery tells us about the process of scientific understanding. Science is often presented as a march of progress, a steady accumulation of facts and theories building toward complete knowledge. The reality is more complex and more interesting. Scientific understanding advances in fits and starts, with long periods of incremental progress punctuated by sudden breakthroughs that reframe everything that came before. The discovery of BetelBuddy is one of these reframing events. For decades, astronomers looked at Betelgeuse and saw a single star with puzzling behavior. Now we look at the same data and see a binary system whose properties make perfect sense in light of the companion's presence. The facts have not changed, but our interpretation of them has shifted fundamentally. This pattern repeats throughout the history of astronomy. Before the 1990s, we knew of exactly one planetary system, our own. Then came the first detection of exoplanets, and within a few years we realized that planetary systems were ubiquitous, transforming our view of Earth's place in the cosmos. Before gravitational wave astronomy, we could only study the universe through light. Now we have a new sense, one that reveals phenomena invisible to any telescope. BetelBuddy represents a similar shift on a smaller scale. The recognition that many, perhaps most, giant stars have companions that influence their evolution and appearance opens new lines of inquiry and explains previously mysterious observations. It is a reminder that the universe is more complex, more interconnected, and more surprising than our models often assume. The story of BetelBuddy also highlights the value of long-term, patient observation. The data that revealed this companion spans more than a century, gathered by thousands of observers using instruments ranging from the human eye to space telescopes. No single observation campaign could have accomplished this. The discovery emerged from the accumulated effort of generations. In an age of instant communication and rapid results, there is something valuable about endeavors that require patience measured in decades. The universe operates on its own timescales, indifferent to human urgency. If we want to understand it, we must sometimes match our efforts to its rhythms, watching and recording and waiting for patterns to emerge. This is one reason why astronomical archives are so precious. The plates and logbooks and databases of past observations contain information whose full significance may not be apparent for years or decades. Every careful measurement contributes to a collective enterprise larger than any individual project. The astronomers who first noted Betelgeuse's brightness variations in the 1800s could not have imagined that their work would help reveal a stellar companion 150 years later. But their contributions were essential. As we approach the end of this exploration, let me offer some thoughts on what BetelBuddy means for the broader human enterprise of understanding the universe. We live in a remarkable time for astronomy. New facilities and techniques are revealing aspects of the cosmos that were completely inaccessible to previous generations. We can see farther, measure more precisely, and simulate more comprehensively than ever before. Yet, for all our advances, the universe continues to surprise us. BetelBuddy was not predicted. No one expected to find a companion around Betelgeuse that explained its long mysterious variability. The discovery emerged from data, from patient analysis, from the willingness to question assumptions and consider new possibilities. This is how science works at its best. We build models and theories that explain what we know. Then we probe deeper and find that reality is richer than our models suggested. Each surprise is an opportunity, a sign that there is more to learn and understand. The gaps in our knowledge are not failures but invitations. BetelBuddy also reminds us that the universe is full of relationships. Stars pair up, planets orbit stars, moons circle planets, galaxies cluster together in vast cosmic structures. At every scale, gravity binds objects into systems, and these systems evolve together over cosmic time. The lonely wandering star, unattached and unaffected by others, is the exception rather than the rule. For Betelgeuse, this companionship has shaped its entire existence. The 400-day pulse that caught astronomers' attention is a rhythm beaten out in partnership, a gravitational duet performed across millions of years. When we look at Betelgeuse's light, we are seeing not just one star but two, their fates intertwined in ways we are only beginning to understand. The next chapter of this story will be written by the supernova. Somewhere between tomorrow and 100,000 years from now, Betelgeuse will collapse and explode, briefly outshining all the other stars in the galaxy combined. For observers on Earth, this will be the astronomical event of a lifetime, something witnessed by perhaps a few billion people alive at that moment and never to be seen again for thousands of years. BetelBuddy will be there, close enough to feel the fury of the explosion, far enough perhaps to survive it. What happens next depends on details we cannot predict with current knowledge. But whatever the outcome, the Betelgeuse BetelBuddy system will transform into something new, something different, something worthy of its own chapter in the continuing story of cosmic evolution. For now, we watch and wait, gathering data, refining models, preparing for the spectacle to come. The discovery of BetelBuddy is not an ending but a beginning, a new foundation for understanding one of the most dramatic star systems in our galactic neighborhood. Astronomers young and old are pursuing the questions that this discovery has opened, confident that more surprises lie ahead. That is the nature of science, always looking, always questioning, always open to the unexpected. BetelBuddy teaches us that even familiar stars can hide secrets, that patient observation pays dividends, and that the universe rewards those who look closely and think carefully. High in Orion, the shoulder of the hunter continues to glow, its light a mixture of the giant and its hidden partner, a beacon visible to anyone who lifts their eyes to the winter sky. For millennia, humans have looked at that light and wondered, Now we know a little more about what we are seeing, and that knowledge only deepens the wonder. The dance of Betelgeuse and BetelBuddy continues.